Welcome to solverfy.
Okay, so number 6 wants you to look at, basically repeat the process of example 2 in the text in chapter 43, but do it with an alpha particle instead of a proton. And it wants you to calculate what the maximum energy that alpha particle can attain and what would its speed be. So for part A, we're looking at, so from example 2, let's go ahead and write down what example 2 gives us. Example 2 gives us that the kinetic energy of a particle in a cyclotron is going to be equal to the charge of the particle times the magnetic field squared. Charge of particle squared times the magnetic field squared times the radius of the cyclotron squared, divided by 2 times the mass of the particle, which is equal to the kinetic energy, the classical kinetic energy, 1/2 mv squared. So for an alpha particle is going to basically be a helium nucleus. So 4 particles, 2 protons, 2 neutrons. So it's got 2 protons and 2 neutrons. Now, the mass of a proton is equal to the mass of a neutron. So we can basically say this is just 4 times the mass of, so the mass of an alpha particle is just equal to 4 times the mass of a proton. So now let's go ahead and plug in these values into this equation here. So we have K is equal to the charge squared. So now the charge of an alpha particle, it has 2 protons instead of 1 proton, and 2 neutrons, which are chargeless. So it has a charge of 2. So 2q squared b squared r squared, since the magnetic field and the radius of the cyclotron stay the same, divided by 2 times 4m. So which is the mass of the alpha particle, which is 4 times the mass of the proton. So this is going to be 4q squared b squared r squared over 2 times 4m. Okay, so let's go ahead, these cancel out, and that brings you right back to your original expression. So the charge to mass ratio is going to be the same. So it's going to be 1 to 1 as well. So the kinetic energy of an alpha particle, the maximum kinetic energy of an alpha particle is going to be equal to the maximum kinetic energy of a proton. So, which is given to you in example 2 as 8.7 MeV. Now, to calculate the velocity, we just solve for V from this expression here. So V is just equal to the square root of 2K over M. So this is equal to the square root of 2 times 8.7 MeV times 1.6 times 10 to the minus 13 joules per MeV divided by 4 times the mass of a proton, 1.66 times 10 to the minus 27 kilograms. All right, so now we need to convert to joules because the mass of the proton is given in kilograms. And if you see, so this conversion is usually 1.6 times 10 to the minus 19 joules per electron volt. But since I kept this in mega electron volts, which is 10 to the 6th electron volts, I just added 10 to the 6th to 10 to the minus 19 to give 10 to the minus 13. So this works out to basically to be approximately 2.0 times 10 to the 7th meters per second. Let me clean that up a little bit. times 10 to the 7th meters per second. So a small fraction of the speed of light. So now for part B, wants you to repeat this again, but with a deuteron, which is just a stable isotope of the hydrogen atom, which is just it has a hydrogen atom with a neutron, so it's got one neutron and one proton. So the mass, I'll just call this mass of D is equal to 2 times the mass of a proton. So now we can plug this in, and then also the charge of a deuteron is just equal to the charge of a proton. So the charge on a proton is equal to charge of a deuteron, because it's just still got one proton. So plugging this into our expression from before, K is equal to Q squared, B squared, R squared, divided by 2 times 2m. So the charge to mass ratio is going to be 1/2 so the charge to mass ratio gives the fact that the kinetic energy is 1/2. The kinetic energy of a deuteron is equal to 1/2 of the kinetic energy of a proton. So now for which is going to be equal to 1/2 times 8.7 MeV, which is equal to 4.35 MeV. So now the velocity of this particle, of a deuteron, the maximum velocity is given by square root of 2k over m, which is equal to square root of 2. I'm going to leave this in 1/2 for the purpose of expressing the problem here. I'm going to leave this like this: 1/2 times 8.7 MeV times 1.60 times 10 to the minus 13 joules per MeV divided by 2 times 1.66 times 10 to the minus 27 kilograms. All right, so now these 1/2s cancel. So now the energy to mass ratio is going to be the same as the energy to mass ratio of an alpha particle. So if you work all this out, you find that this is the same velocity, 2.0 times 10 to the 7th meters per second. And now for part C is, in each case, what is the frequency of the voltage required? So we're also given in that example that the frequency of the voltage required is equal to the charge particle times the magnetic field divided by 2 pi times the mass. So the charge to mass ratio, so the magnetic field and 2 pi are constant. So we can say that this is actually, so B over 2 pi, if we pull the constants out, times Q over M. So ratio that makes a difference. So for an alpha particle, this is going to be 2Q over 4M, which is equal to 1/2 Q over M. So the frequency is going to be equal to, so the frequency of an alpha particle, frequency required for a proton, which has been given in example 2. So we'll simplify this: 1/2 times 26 megahertz, which is equal to 13 megahertz. Now for a deuteron, the charge to mass ratio is Q to 2m, which is equal to again, 1/2 Q over m, so 1/2 the charge to mass ratio of a proton. So the frequency of a deuteron is going to be equal, again, to 1/2 the frequency of an alpha particle, which is equal to, again, 13 megahertz.